Alright, so, interesting. Chapter 20, number 1, in the Cotnell and Johnson book published by Wiley. Defibrillator is used during a heart attack to restore the heart to its normal beating pattern. Defibrillator passes 17 amps of current through the torso of a person in 1.5 milliseconds. How much charge moves during this time? Okay, so we know current is delta Q over delta T. So they're asking for that. So current times delta T will give us delta Q. Of course, that's going to be 17 amps times, careful on this one, 0.0015 seconds. Turn the 1.5 milliseconds into, move it 3 places to the left. Do that, and assuming we can trust the answer that they give us, we get 0.0255 coulombs worth of charge. Alright, how many electrons pass through the wire? Well, if there's that much charge, remember charge is carried in discrete amounts of 1.6 times 10 to the negative 19th coulombs for every electron. So if I take the amount of charge here, 0.0255, divided by 1.6 times 10 to the negative 19th, I should get the number of electrons. .0255. Is that correct? Yes. Divided by 1.6 to the 10 to the negative 19. Equals. I love the way this. Yeah, thank you for making me count all that out. I'm assuming we can leave it as 1.59 whatever times 10 to the 17th. 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yes. It's ridiculous. Okay. So, and number 10 from the Wiley packet, chapter 20. A large spool in an electrician's workshop has 77 meters of insulation-coated wire rolled around it, or coiled around it. The electrician connects a battery to the ends of the spooled wire. The resulting current is this. Some weeks later, after cutting off various lengths of wire to use for repairs, the electrician finds that the spooled wire carries this much current when the same battery is connected to it. So, here's what I would suggest. We've got two things going on here. We've got, let's go situation 1, situation 2 later on. And in situation 2, by the way, the length of the wire is less than it was in 1. It's cut off pieces. Now, what does the length of the wire affect? All right. One of the overarching things here is that the resistance is determined by the resistivity of the material not given to us, right? Which is a little unnerving, but that's okay. Times the length divided by the area. Or did I reverse that?
That's right.
That's right. More length would be more resistance, more area would be less resistance. Yes, that's right. So, but there are two resistances because there are two different lengths. Now, the resistivity and the cross-sectional area is the same because it's the same wire, so made of the same stuff and has presumably the same thickness. So, R1 is equal to rho L1 over A. I do not have to call rho or A with a little 1 because they're the same each case. Whereas R2 is going to be rho L2 over A. But that's still not enough to really get me where I need to go because they talk about current and voltage and stuff. So let's go to Ohm's law. Delta V is equal to I R. but there is a I1 and an R1. They tell us the I1. One of the few things they do is they say the first time he does it, the current's 2.4 amps. And we already know that because there's a different length, there's got to be a different resistance. What about the voltage? He hooks it up to the same damn battery or whatever, right? So the voltage actually doesn't get a 1 or a 2, it's the same. Delta V over same delta V produces a different current, understandably, because there is a different resistance. If I've changed this and this stays the same, then this has to change. So this is equal to delta V, and this is equal to delta V. So I set them to equal to each other. So I1 R1 equals I2 R2. And now we're going to replace resistance with what we wrote up above, which is going to be I1 times rho L1 over A. Cool. Equals I2 times rho L2 over A. But the rho and the A gone, right? They divide at / multiply out, however you want to look at it. And I end up with I1 L1 equals I2 L2. Exactly. And then we would solve that off for L2 is what we want, right?